And let me just recap what we talked about on Monday. So we introduced the WKB method. And the idea is that for problems of this form, and in particular, we took an epsilon squared out in front. So we have some singular term here as you take epsilon to 0. The WKB ansatz is that you assume y has the form y is asymptotically approximated as theta x over e to the alpha, or epsilon to the alpha, y0 of x plus epsilon to the alpha, y1 of x, so on, as epsilon goes to 0. And alpha is going to be some positive power. Typically, you're going to generate some hierarchy of equations then that's going to be solvable. And you're going to need to solve for theta and y0 for a first order expansion. And as we showed, you just plug in this ansatz, you expand, you collect terms in the hierarchy, you choose alpha in order to match the leading order terms, and then you'll have hopefully a solvable hierarchy of equations that you can then work out. So the example that we showed, we were able to write down explicitly the formulas for the first order solution, and in particular, in that case, you could also get an exact solution to the formula by performing a change of variables. And the point which I sort of muddled a little bit is that the first term expansion that we derived is an excellent match to the Bessel function solution that you can derive using the change of variables. Okay, so so in order to measure the error of the WKB expansion, you have to go to higher order than we went for the general example that we took. Okay, so what we found is that if you take alpha equals 1, then you have at order 1 theta x squared equals q of x. This is our iconal equation, and theta of x is equal to plus or minus the integral from 0 to x square root of q of s ds plus theta of 0. At order epsilon, we found that using the iconal equation, we could reduce the order epsilon equation down to theta xx y0 plus 2 theta x y0 prime equals 0. And we were able to solve this for y0 is equal to c over square root of theta x absolute value, q of which is equal to q of x to the minus 1/4. So then y is asymptotically given by, for a first order expansion, q of x to the minus 1/4 a0 exponential of minus 1 over epsilon integral from 0 to x square root of q of s ds plus b0 exponential of 1 over epsilon integral from 0 to x square root of q of s ds. And this is not something that you could arrive at by using sort of a standard approach. You need this special ansatz in order to get this, because in particular, it's this function of theta of x, which could be, you know, it's an integral over your functional coefficient of the lowest order term here. And this would not come about by using sort of just regular perturbation expansion type methods. Okay. So what we might get to today is talking about what's called turning points. Okay. But I want to just finish up what I was talking about with respect to error measurements. So in general, okay, if we want to measure our error, we need to look at order epsilon squared. Okay. And so I'm gonna go back to writing down the full expansion that we wrote down on Monday. Okay. If we sub in the WKB ansatz, okay, what's been generating our equations of each order is the following expanded equation. Sort of epsilon squared plus 1 over epsilon theta xx y0 plus 2 theta x y0 prime plus theta x squared y1 minus q of x y0 plus epsilon y1 plus epsilon squared y2 here is equal to 0. Okay, so so the terms of next order are going to be our order epsilon squared terms, and those are going to allow us to estimate how much error we're making with this leading order expansion. So in particular, it's going to have a similar form to our order epsilon problem, and we're going to be able to use the iconal equation in order to cancel out these terms here, right? So these cancel by the iconal equation. Okay, and if we make the ansatz that y1 is equal to y0 times some function w, which is a function of x, then what we end up with is 2 theta x y0 w prime plus y0 prime prime is equal to 0. Okay, now we're going to make a specific assumption that q of x is greater than 0 first. And in that case, theta sub x is going to be what? Let's look back at theta. Okay. If q of x is positive, we can assume that theta sub x or theta x is going to be
real,
at least real, right? If q of x is negative, then theta sub x is going to be imaginary. Okay. And this distinguishes two different types of solutions that you can get with the WKB ansatz. If q of x is positive, then you're going to have exponentially growing or decaying solutions. if Q of X is negative, you're going to have oscillatory solutions. Now, what if Q of X changes signs? Well, then you have what's called a turning point problem, and you have to stitch together exponentially growing and oscillating solutions. Okay, and that's what we'll talk about in a little while. Okay, so in this case, theta sub x is real. Okay, so 2 theta sub x y0 w prime equals minus y0 prime prime. We can write this as 2c theta sub x w prime over square root of theta sub x using the solution that we have for y0 minus d2 dx squared c over square root of theta sub x is equal to d dx c theta sub xx over 2 theta x 3/2. Okay. And if we write this by isolating w prime, then we have a fourth d dx theta xx over theta x 3/2, 1 over square root of theta x. So this means that w of x is equal to a fourth integral from 0 to x d ds theta ss over theta s to the 3/2, 1 over the square root of theta s ds plus w evaluated at 0, okay, which we don't know yet. Okay, so so we can simplify this a little bit by writing w of x equals a plus a fourth theta xx over theta x squared plus an eighth integral from 0 to x theta ss squared over theta s cubed ds. Okay, and the point is that we can get some expression for w of x in terms of theta. Now we don't know what q is, okay, so we're not going to know exactly what theta is, but the point is we can get some expression for w, which allows us to compute y1, okay, which is going to be our next order corrective term. And if we expect this to be an asymptotic series, then we would hope that y1 will be asymptotically smaller than y0, okay? Now there's another case, which is that if q of x is less than 0, then as we said before, we're going to have theta x equals plus or minus I times the square root of the absolute value of q of x, okay? Then in this case, theta xx is equal to plus or minus I over 2 minus qx absolute value divided by square root of the absolute value of q, or minus plus or minus or plus I q sub x over 2 square root of absolute value of q. So then theta xx over theta x squared is equal to minus or plus I qx over 2q square root of absolute value of q, or plus or minus I q sub x over 2 absolute value of q to the 3/2. Okay. So just trying to clean up that expression a little bit. So theta xx squared equals minus qx squared over 4 absolute value of q equals qx squared over 4q. And theta x cubed is equal to plus or minus I cubed q to the 3 halves absolute value to the 3 halves. So we have theta xx squared theta x cubed is equal to qx squared over minus plus 4I q absolute value of q to the 3 halves. This is equal to minus or plus I qx squared over 4 absolute value of q to the 5 halves. Okay. So consequently, okay, we can write out these long expressions for w. Okay. So w of x is going to be equal to a plus 4 different cases. Okay. And I'll think I should be able to fit them all in here. Qx over q to the 3 halves plus 1 over 32 integral from 0 to x qs squared over q to the 5 halves ds. Okay, and theta x is equal to, this is whenever theta x is equal to the square root of qx, or in other words, when qx is positive and you take the positive part of that square root. Okay. Alternatively, you could have minus an eighth q sub x q to the 3 halves. Okay, minus 1 over 32 integral from 0 to x qs squared over q to the 5 halves ds. This would be if you take theta x equals minus square root of q of x. Okay, so those are the real part cases. And then we have I q sub x over absolute value of q to the 3 halves minus 1 over 32 integral from 0 to x I qs squared over q to the 5 halves. So this is when theta x is equal to I square root of q, and then absolute value of q. Okay, and then lastly we have minus an eighth I qx over absolute value of q to the 3 halves plus 1 over 32 integral from 0 to x I qf squared over q 5 halves, absolute values around that, sorry, ds. So theta x equals minus I q of x with absolute values. Okay. So this means that, yeah.
In the first case, what is the denominator on the integral?
Oh, this is q to the 5 halves.
Okay.
Yeah, so these are all q to the 5 halves, except, you know, down here we have to take the magnitude because q is going to be negative in this case. So we're, yeah. So because we know that q is order 1, as long as q doesn't become 0 at any point, right, all of these expressions are going to be order 1. And so we can expect that we're going to have a nicely ordered asymptotic series. Okay, so all this sort of messy work is just showing that y1 is going to be properly ordered in our asymptotic series. So for small epsilon, the WKB ansatz is well ordered as long as epsilon y1 is much less than y0. Okay, or in other words, if as long as, you know, epsilon w of x is much less than 1. Okay, so so I'm going to need to grab a new page. Did people finish writing this down? If, well, assuming they wanted to. Okay. All right. So let me just summarize this so that, you know, this is just reminding us that, yeah, we are trying to build asymptotic series here, and we want to make sure our first order approximation is a legitimate asymptotic approximation. Okay, So it's going to be well ordered, okay, as long as epsilon y1 is much less than absolute value of y0, okay, or in other words, that epsilon w is much less than 1, okay. So in terms of q of x and its first derivatives, okay, for some interval x that goes between x0 and x1, okay, we have an accurate approximation as long as the following thing is true: epsilon, absolute value of a, plus 1/32 q sub x, q to the 3/2 times 4 plus integral from x0 up to x1 q sub x over q dx, as long as this whole thing is much less than 1, okay, where let's say we're taking that this magnitude signifies the infinity norm, okay, over x0, x1. Okay, so as long as this is all well behaved, which means that you can't have q vanish, okay, and you can't have infinite derivatives, okay, you have sort of adequate smoothness and same sign of q. Now the issue is going to come up with turning points, right, where q switches sign, and there we have to more surgically sort of handle what happens at these interfaces of the solution where q is crossing through 0, and that's what we're going to deal with next, okay. But just to sum up, so this is going to hold, okay, if this interval of x does not contain a turning point, okay. And another thing to note is that in general, we need to check that A0, B0, and A don't depend on epsilon, okay. And that's going to be problem dependent, okay, but in general that's not going to happen. But yeah, you have to check it sort of case by case in order to make sure everything works out, okay. So that's the ordering of this. That's just sort of crossing T's and dotting I's on the fact that this works as a legitimate asymptotic approximation, okay. So the next thing I want to talk about then is how to deal with these turning points, okay. And the main issue is how you select your coefficients. And as you might imagine, you sort of have to choose your coefficients to match. So just like we do in other asymptotic methods, okay, you would hope that you should have enough free constants in your asymptotic approximation that you can have a nice, continuous approximation that is continuous, across the whole domain that you're concerned with, okay. Now, turning points can happen even if, q of x is smooth, okay. And in particular, we're going to look at the case where it just has a simple 0, okay, at, let's say, some point x prime, okay. And we'll say that lives between 0 and 1, okay. So that is q of x prime is equal to 0. And it's simple, which means that q prime of x prime is not equal to 0, okay. So it's not like some minimum coming down and grazing 0 or something like that. You're crossing through 0, Okay. And we'll say that x lives between 0 and 1, just on the unit interval. Okay. And just for illustration, we'll take this crossing to be an increasing part of Q. So you're going from negative to positive values of Q for the example that we'll look at. Okay. So for example, okay, we're going to take Q prime of x prime to be greater than 0. Okay. And so here's our Q here, and it looks like this. So here's x, here's Q of x, and here's our x prime here. Okay. So over here, right, Q is less than 0, and over here, Q is greater than 0. Okay. And so we are going to have oscillatory solutions over here, right? Because theta sub x is going to equal to plus or minus I square root of absolute value of Q. And theta of x is going to be plus or minus square root of Q over here. And they're going to be exponential solutions, okay? For x is less than x prime, and over here is x is greater than x prime. Okay. So we're gonna connect these together. Okay. And we'll see how that sort of matching process happens. Okay. Now, the main thing that you derive in this case is what's called connection formulas. Okay. And that just tells you how to relate the coefficients of your left and right solutions when you have a single turning point. Okay. So let's go ahead and say, well, we're going to apply our WKB ansatz, okay, to x is less than x prime and x is greater than x prime, okay? So in that case, to leading order, y is going to be this thing YL, okay, for x is less than x prime, and YR for x is greater than x prime, okay? And YL, I'll write it out, is going to be 1 over Q of x to the 1/4, okay? A L exponential of minus I over epsilon integral from x up to x prime square root of absolute value of Q of S ds plus BL exponential of 1 over epsilon or I over epsilon integral from x up to x prime square root of absolute value of Q of S ds. Close everything up, okay? And you could take this and also write it in terms of trig functions, right? Because you have complex exponentials, okay? So we could equivalently say, well, let's just put a tilde on these, and I'll write this as 1 over Q of x to the 1/4 AL cosine of 1 over epsilon integral from x up to x prime over square root of Q of absolute value of Q of S plus BL sine 1 over epsilon integral from x up to x prime square root of Q of S, okay, ds. Okay. So that's our oscillatory solutions that are on the left because we have our functional coefficient is negative in that case. On the right, we're going to have exponential solutions. So we have 1 over Q of x to the 1/4 AR exponential of minus 1 over epsilon integral from x prime up to x, square root of q of s ds plus br exponential 1 over epsilon integral from x prime up to x, square root of q of s ds. Okay. And the point is that a l, we'll say tilde, bl tilde, ar, br are not independent. Okay. So we must match YL and YR at x equals x prime. Okay. So just like we've done with matched asymptotics before, okay, we just have to look at what happens as you approach this boundary. Okay. So we're going to do that through a transition layer. Okay. Let me see how far I can get with this today. But the idea is that we're gonna write down some rescaling of x, and we're gonna do the matching in that rescaled variable. Okay. So if we build some transition layer, like we've done before for matched asymptotics, we write down x tilde equals x minus x prime over epsilon to the beta. Okay. Or in other words, x is equal to x prime plus epsilon to the beta x tilde. Okay. So we're squashing the scaling of x in right at this boundary layer. It's not exactly a boundary layer, but it's the interface between these left and right solutions. So we'll expand q of x to q of x prime plus epsilon to the beta x tilde. This is going to be equal to q of x prime, which of course is going to be 0, plus q prime of x prime, which is going to be positive epsilon to the beta x tilde plus some higher order terms. So I can write this then as epsilon to the beta x tilde q prime x prime approximately. Okay. And we're going to go ahead and assume that we have some inner solution y of x tilde here. Okay. Well, then d dx is equal to 1 over epsilon to the beta d dx tilde. And this means that epsilon to the 2 minus 2 beta y prime prime minus epsilon to the beta x tilde q prime of x prime plus higher order terms times y is equal to 0. Okay. Now recall that epsilon squared y prime prime minus q of x y is equal to 0. So that's where we're getting this above expression. Okay. Now the question is, once we have this system, how do we balance things out and solve it? Okay. Well, what we'd like is that epsilon to the 2 minus 2 beta match up with epsilon to the beta. Okay. So we need 2 minus 2 beta to be equal to beta. So our transition layer is going to have an epsilon scaling of epsilon to the 2/3. Okay. And then we'll take y to be potentially some different scaling. in terms of its amplitude. Okay. So at order epsilon to the 2/3, which is going to be our first order in this equation, we have y0 prime prime minus x tilde q prime x prime, which is just going to be a constant. Y0 is equal to 0. Okay. And x tilde in this case is just going to be on the real line because we have this stretched inner layer, right? This transition layer that's happening right at x prime. Okay. Now, if I make a change of variables, okay, I can take s is equal to q prime x prime to the 1/3 x tilde. I end up with d2 y0 over ds squared minus s y0 is equal to 0 on the real line still. Okay. And this ends up being Airy's equation. Okay. Now we can solve Airy's equation in a number of ways. Okay. Let me just walk through that, and then we'll get some asymptotic expansion for Airy's equation. Okay. The idea here is that this inner solution, right, is gonna properly connect together the right and the left solutions that we have bridging across our transition layer. You don't always necessarily have to do this. For instance, you'll have an example on your homework where if you just actually have a jump discontinuity in Q, then things get a lot quicker because you don't have to worry about how Q is approaching the zero, the simple zero that it has. If it just has a jump discontinuity, okay, the scaling of Q as it gets closer and closer to zero matters less. Okay, but here you really have to track that, and that's given in particular by this Q prime of x prime here, the slope of your function here. So that matters as far as how the solution is shaped at this transition layer in between the left and right solution. Okay. So, okay, fine. So this is Airy's equation. Okay. And we'll just sort of do a power series method in order to get these Airy solutions. Okay. And so to solve Airy's equation, we're going to go ahead and take y0 of s is equal to the sum from n equals 0 up to infinity of an s to the n. Okay. So if we plug this in, we end up with the sum from n equals 2 up to infinity n times n minus 1 an s to the n minus 2. That's the second derivative term. And then our first derivative, or our 0th derivative term, becomes an, and then we have this extra power of s that gets tacked on. Okay. Now, if we shift the index of the first sum, okay, pull out 2 times a2, and if we shift index of the second sum, we end up with 2a2 plus the sum from n equals 1 up to infinity of n plus 2 times n plus 1, an plus 2 minus an minus 1. Okay. So like with these power series methods, the idea is to get some recursion relation for your coefficients. Okay. So so we find that a2 needs to be 0, and an plus 2 more generally is an minus 1 over n plus 1 times n plus 2, and this holds for n equals 1, 2, 3, 4, so on, so on. Okay. So we get like A3 is equal to A0 over 2 times 3. A6 then is equal to A0 over 2 times 3 times 5 times 6, okay? A9 is equal to A0 over 2 times 3, 5 times 6, 8 times 9, okay? So we need to be able to write down some sort of pattern for that. And also A4 is equal to A1 over 3 times 4. A7 is equal to A1 over 3 times 4 times 6 times 7. And A10 is equal to A1 over 3 times 4, 6 times 7, and 9 times 10. Okay. So our functions then, in this case, our array functions, are going to be given by the power series that you get by either taking A0 to be A0 to be 0 or A1 to be 0. Okay. So in other words, the AI array function is AI of 0, 1 plus s cubed over 6, right? Plus the s to the 6th term and so on, plus AI prime of 0s plus s to the 4th over 12, and so on, okay? And we also have another array function, okay, which is going to be some linear combination of these power series. Okay. This is one way to derive the power series expressions for your array functions, right? You can also get these asymptotically, asymptotic approximations. Okay. So so if we want a function, okay, that has that AI goes to 0 as s goes to positive infinity, okay, we need to take that AI of 0 is equal to 1 over 3 to the 2/3 and gamma function of 2/3. And I'm running out of space here. So, and then AI prime of 0 needs to equal, and I'll write this down. AI prime of 0 is equal to minus 1 over 3 to the 1/3 gamma of function of 1/3. Okay. Your power series expression then for your array function is 3 to the 2/3 pi sum from k equals 0 up to infinity 1 over k factorial gamma of k plus 1 over 3 sine of 2 pi over 3 k plus 1 3 to the 1/3 s to the k. Okay. So it's something of a mess. It requires some massaging to go from the power series expressions we had before to this, but you can see in here this power series of s that we end up with. Okay. And it's gonna zero out for particular values of k, so that you're only gonna have the s to the 3rd, s to the 4th. You're gonna skip the s squared and the s to the 5th and so on. Okay. And so we'll just say this requires some massaging to get, okay? All right. And then we can also take EIS, okay? To be just some linear combination of different forms of the AI array function. I won't write out the lengthy expression for that, okay? But this is the form of that other array function, which is going to be linearly independent. And if we set psi equal 2/3 s to the 3/2, we can write the array functions asymptotic approximations as 1 over the square root of pi s to the 1/4 cosine of psi minus pi over 4 plus 5 over 72 psi sine of psi minus pi over 4 as s goes to minus infinity, and then 1 over 2 square root of pi s to the 1/4 e to the minus psi 1 minus 5 over 72 psi as s goes to positive infinity, okay? And okay, yeah, this long derivation, it's something of a headache, but I want you to notice that what we've arrived at now is that on either side of the transition, we either have an oscillatory solution, okay, as s goes to minus infinity, which would be left of the transition point, okay, or an exponentially decaying solution on the right-hand side of the transition point, okay? So by sort of unfolding things right around this transition point, we're able to come up with something that we can allows us to sort of stitch together the left and right half solutions. BI is going to be something similar. Okay, it's going to be some lengthy expression, 1 over square root of pi s to the 1/4 cosine of psi plus pi over 4 plus 5 over 72 psi sine psi plus pi over 4, okay, as s goes to minus infinity. And then we have this 1 over square root of pi, absolute value of s to the 1/4 e to the psi 1 plus 5 over 72 psi. Okay. And then as s goes to positive infinity. Okay. All right. So you see these sort of complementary parts of the exponential, and also the oscillatory solutions. Okay. Now, what we're going to find is that we should have 6 undetermined coefficients. We should have the coefficients of our outer solutions in the left and right hand sides, right? We need some of those coefficients in order to be able to satisfy boundary conditions in the full problem. But we also need those coefficients in order to provide proper matching between the outer and the inner solutions, okay, as we cross across this transition point. And that's going to be our connection formulas, okay? So so not on Friday, because Friday is going to be our sort of practice problem day, but on Monday, next Monday, we'll show how to stitch these together. But I think the general ideas here should be enough for you to get started on the transition layer problem on the homework if you want to. And then we'll wrap up with wave propagation and energy methods, and that'll kind of be the last of WKB. We should finish up towards next week. Okay. All right. So any questions about WKB transition layers?
You might have said this already, but so with these asymptotic approximations for the solutions to the area equation, we use that just to match, and then in the transition layer we use the power series solution to
Yeah.
approximate.
Right. So within the transition layer, you need the full power series, right? Or you can just use the Airy functions, right? Um, but yeah, as you go out to negative and positive infinity, the asymptotic approximations become more and more precise, right? Because they should hold precisely as you go out to positive and negative infinity. Okay, so it's just a much cleaner way to do your matching as you go out of the transition layer, rather than having to do it with the Airy function, which you're going to get some implicit equation that's going to be hard to deal with. Okay.
The index on the area equations, like a sub I, b sub I, what does changing I do? I just didn't see where that was.
Oh, this is like the name. So the full name of this function is AI and BI. Yeah, this is called the Airy function, and I think this is called like the Berry function, because they weren't very inventive with the other name. But there's really two Airy functions, but they just decided to call them AI and BI. Yeah.
Okay, gotcha. So it's not like a Bessel function of a certain order.
Yeah, no, it's not like your indexing of the Bessel functions. Yeah.
Okay.
J, K, and I, and then all their indices and stuff like that. Yeah.
Do
There's
they
only two Airy functions. Yeah.
do they also use like the language of the first kind and the second kind or something?
No, it's
That-
just
like they do with Bessel J I and YI.
I don't think so. I think there's just Airy functions, but yeah,
I've just heard Airy and Berry when I've
Yeah.
seen them up.
I think it's the first and second kind stuff is for yeah, Bessel functions.
We also have I don't know if this is a general thing or just a trend, but a lot of times when there's the first and second kind, the second kind blows up at 0, and I don't think that happens with the Airy functions.
Yeah, I think they're both well behaved at 0, and then they should also tend to 0 at as you go out to positive infinity, and they're bounded either direction, right? So you can see here that these are not going to tend to 0, but they'll just oscillate.
Does the Berry function go to infinity as you go to?
Oh, sorry. Yeah. So that's true. The Berry function goes to positive infinity, whereas the Airy function goes to 0. Yeah. Right. Yeah, that's going to blow up. And I think you can also relate the Airy functions to Bessel functions. There's a lot of different expressions for them. So yeah. I think the power series approach is maybe to me, it's the most straightforward way to get at least some kind of expansion for them. But then you have to do some massaging to get the right formulas for the coefficients. Yeah. All right. Okay, so I'll send out this practice problem, and then we'll just have a practice problem session on Friday. We can do question and answer on WKB as well. So I'll see you all then.
Thanks, Zach.
Thanks.